In this module, we continue the discussion of multi-component systems by introducing ideal dilute solutions. We now focus on dilute binary liquid mixtures or solutions. In a binary solution, there are two components. Solvent. This is the component present in a larger amount. For our discussion, we will refer to it as component A. Think of the solvent as the medium that other substances dissolve into. Solute. This is the component present in a smaller amount. We will call it component B. Essentially, it's what gets dissolved into the solvent. In dilute liquid solutions, the concentration of solute B is relatively low. In such systems, even if the mixture doesn't strictly adhere to ideal behavior, Raoult's law tends to be applicable to the solvent. This law becomes increasingly accurate as the solute concentration decreases and the solvent closer resembles its pure state. As it was said, the closer the solvent is to being pure, the better Raoult's law predicts its behavior. Besides Raoult's law, there is another law describing the behavior of liquid solutions. William Henry in the early 19th century explored the solubility of various gases in water. He discovered a direct relationship between the partial pressure of a dissolved gas above a liquid and its concentration within the liquid. This led to the formulation of Henry's law, which can be expressed by this equation. Here, Pb represents the partial pressure of the solute B above the solution, Xb is the mole fraction of the solute in the solution, and Kh is the Henry's law constant. The Henry's law constant Kh is empirical in nature. It is derived from experimental observations rather than theoretical principles. The value of Henry's law constant is determined by the inherent nature of both the solute and solvent. This graph shows an example of the vapor pressure as a function of the mole fraction for a component in a real non-ideal liquid mixture. When a component acts as a solvent and it's almost pure, its vapor pressure is proportional to the mole fraction with a slope given by the vapor pressure of the pure component, as described by Raoult's law. When it is a minor component or solute, its vapor pressure is still proportionate to its mole fraction, but the constant of proportionality is now Henry's law constant. In other words, the vapor pressure of the solute follows Henry's law when its mole fraction is small. Henry's law is more accurate for dilute solutions. The lower the mole fraction of the solute B in the solution, the better it follows Henry's law. While no simple model can capture the nuances of every real solution, we can approximate their behaviors in certain circumstances, particularly when solutions are dilute. In such dilute solutions, solutes tend to deviate from the ideal behavior described by Raoult's law. Instead, their behavior can be accounted for by an empirical approach proposed by Henry's law. This idea is implemented in the model of the ideal dilute solution. It assumes that an ideal dilute solution meets two conditions. The solvent follows Raoult's law, the solute, on the other hand, follows Henry's law. This dual approach provides a practical framework to understand the properties of real solutions if they are sufficiently dilute. Central to this model are two limiting laws, Raoult's and Henry's. Both these laws define the ideal behavior in their respective domains. Raoult's law characterizes the ideal behavior of the solvent in high concentrations, while Henry's law captures the ideal behavior of the solute at low concentrations. This figure illustrates a microscopic representation of an ideal dilute solution. In a pure solvent representing its ideal state, molecules are surrounded only by molecules of the same type. When solute molecules are introduced into the solvent, the environment for these solvent molecules remains relatively unchanged. They continue to be primarily surrounded by their own kind, replicating the surroundings they experience in a pure state. This behavior is visualized in the figure where the blue spheres, representing solvent molecules, remain predominantly surrounded by similar molecules just as they would in their pure form. On the other hand, solute molecules in a dilute solution are surrounded mostly by solvent molecules. Their environment differs drastically from that of their pure state, where they would be surrounded by similar molecules. This leads to their non-ideal behavior, which contradicts Raoult's law. The exception to this would be a situation when solute and solvent molecules bear a strong chemical similarity, in which case the solute would also follow Raoult's law. In contrast to the solvent, the molecules of the solute are in their ideal state according to the ideal dilute solution model when they are surrounded only by solvent molecules. This corresponds to an infinitely diluted solution. When the solute's concentration is not too high, their conditions are not very different from the ideal state. Taking this microscopic picture into account, we can say that when the solute's concentration increases while still remaining relatively low, the ideal dilute solution changes quantitatively but not so much qualitatively. The amount of solute molecules in the solution increases, which leads to an increase of the solute's vapor pressure and a decrease in the solvent's vapor pressure. However, the microscopic surroundings of molecules remains largely the same, resulting in the steady linear changes of the vapor pressure. The properties of ideal dilute solutions, in particular as expressed by Henry's law, have significant implications in various fields. For practical applications, this law is usually expressed in terms of molality, B, of the solute. One distinct feature of Henry's law constant is its specificity. For every combination of solvent and solute, there is a unique Henry's law constant. This makes it especially useful in calculating the solubility of gases in various solvents, especially water. For example, each gas, like oxygen, nitrogen, or carbon dioxide, has its unique Henry's law constant that determines its solubility in water. The interesting part about this equilibrium between the gas in the solution and in the gas phase is its often observed dynamic nature. If you have a liquid solution with a particular mole fraction of a volatile component Xb, vapor B will evolve from the solution until the corresponding pressure Pb is achieved. Conversely, a gas B exerting a pressure Pb above a liquid will dissolve in the liquid until the corresponding mole fraction Xb is reached. Consider a bottle of sparkling water. If sealed, an equilibrium establishes itself between the dissolved CO2 in the liquid and the CO2 in the gas phase. But if the bottle remains open, the gas gradually escapes, preventing any equilibrium. Henry's law has profound implications also in biology and physiology. It is essential for understanding processes like respiration, especially under abnormal conditions such as high-altitude mountaineering or diving. One notable application is in the hyperbaric oxygen therapy in medicine, wherein patients are administered oxygen at high pressures. It results in more oxygen dissolving in the blood than under typical conditions. Knowledge of Henry's law is also pivotal when discussing the effects of gaseous anesthetics. An intriguing aspect to think over is the thermodynamic consideration of gases dissolved in liquids. For example, while oxygen can dissolve in water at room temperature and atmospheric pressure, pure liquid oxygen doesn't exist at these conditions. Nonetheless, despite the thermodynamic instability of liquid oxygen, we can still analyze the oxygen dissolved in water thermodynamically.